Hey everybody, this is Chris back again at the Ancient Scholar, and today we're going to do a bit more of a concise discussion. So if you managed to make it through the last video, which is about was almost 40 minutes long, got to the point near the end, and so what I've done here is I'm actually at where we were at the end of the video. I just want to recap real quick. So what we did was we're talking about the quantum numbers, specifically the quantum number L, which is I have right up here, L and M sub L, and how what those do, and how they can be represented. And so what we said was that in the second energy level, okay, it was a case that I used the second energy level, and we know that the second energy level can have two values of L, 0 and 1, and just to recap, L, another name for L is an orbital. All right, another name for L is an atomic orbital. And just to really quickly recap, if L equals 0, we're talking about an s orbital. If L equals 1, we're talking about a p orbital, and if L equals 2, we're talking about a d orbital. If L equals 3, we're talking about an f orbital, 4, G, H, I, J, and so on and so forth. All right. So we left off with the case that we had n equals 2, L equals 1, and M sub L, the magnetic quantum number, can take the value of negative L all the way up to positive L in discrete integer values. So in the case of L equals -1, up here, the only values that M sub L could take are +1, 0, and -1. And so we're talking about a p orbital, and we know from general chemistry that we have three p orbitals, right? We have a px, a py, and a pz orbital, or pz orbital. And we like to think that in chemistry, okay, if this is the x, y, and z axes, all right, so z, x, y, we like to think that the px orbital is kind of a dumbbell shape that's aligned along the x-axis. We like to think that the py is dumbbell shaped and aligned along the y-axis, and then the pz is dumbbell shaped and it's aligned along the z or z-axis, with all the p orbitals taking on kind of a little dumbbell shape like this, with a node in between the two lobes. So it kind of looks like a dumbbell, and that's typically what we're used to seeing. And where I'd left off in the last videos, I said, well, let's just take a look at trying to visualize these quantum numbers a little better and come up with a way of representing them. So what I did is I said, hey, look, we know that the total angular momentum for an electron in a certain state is going to be the big L. That's the total angular momentum equals L plus 1, L times, rather, L plus 1 multiplied by H bar, which is a reduced Planck's constant. So what we did is we took our value of L to be L equals 1, and I said, well, let's go ahead and plug that in. So total angular momentum for our p orbital is going to be the square root of 1, okay, because that's my value of L. 1 plus 1 times 1 plus 1, all of that multiplied by h bar. 1 plus 1 is 2, 2 times 1 is 2. So the total angular momentum for the electron is going to be the square root of 2 times h bar, which is about, what, 1.4 and some change multiplied by h bar. Okay? All right, fair enough. And then we said, well, how about we just look at, so this is just a total angular momentum here. So little l is sort of a way of looking at the angular momentum, at the magnitude of the angular momentum. Okay, so little l is sort of a way of looking at the magnitude All right. Whereas m sub L is a way of looking at how it's oriented. All right, how it's oriented, and we do is we'll choose the z-axis, and we'll talk about how is that angular momentum oriented along the z-axis. And normally in classical mechanics, these concepts are much easier, much more intuitive, because you know if something has, angular momentum, it's moving. We know that the momentum is going to be exactly in that direction, because momentum, okay, p, in classical mechanics is just an object's mass times its velocity, and velocity is just speed in a certain direction. So in classical mechanics, we know exactly the direction, but in quantum mechanics, because we have to deal with the uncertainty principle, we can't excuse me, we can't really know the exact direction. So we have to look at that a little differently. And so what we did is we said, okay, well, now that I know that the total angular momentum, okay, so L equals the square root of 2 times h bar, okay? And then what we want to do is we want to go ahead and we want to look at the orientation along the z-axis. Where is that momentum? Where is kind of the orientation, the direction of that momentum going? And the m sub L, of course, is a way of doing that, because the LZ, okay, the orientation of that momentum along the z-axis is equal to m sub L times h bar. So LZ equals m sub L times h bar. So let's just go ahead and do that really quick. It's really pretty easy in this case. So L sub Z is going to take on 3 configurations, because I have 3 different values for m sub L. Okay, so I have my total angular momentum, L equals 1, that's set. Okay, so I'm dealing with a p orbital, that's set. The total angular momentum we know, but that angular momentum can be oriented in 3 directions, if you will. Because remember, L depends on n, and m sub L depends on L, okay? So if you had no angular momentum, let's say L was 0, you had an s orbital, well, m sub L would axiomatically have to be 0. It couldn't take on any other values, because you would need a non-zero value of L, okay? So you need 1, 2, 3, 4 to have multiple values of m sub L. So the orientation along the z-axis is equal to m sub L times h, and so that gives us 3 different configurations. That gives us plus 1 times h bar, okay, and 0 times h bar, which is just going to be 0, and then negative 1 times h bar, okay, which is negative h bar. So we have h bar, a 0, and negative h. So that's, if we wanted to literally look at that, it would be h bar, 0, negative h bar, okay? And I said we could kind of graphically represent that by, if I drew a circle, so this circle here, and the radius, that's this green line here, the radius of the circle, we'll say that the radius of the circle is going to be the magnitude. So this length of this green line, r here, is going to equal, and I said I use the, let's start at plus 1. Let's start at m sub L equals plus 1 here, okay? Or actually, we'll just before we do the z component, let's talk about the total angular momentum. So the magnitude is the radius of this sphere, this sphere that we drew here. That's this green line here. So the r, I'll just put r there. So r in this case is going to equal, okay, the square root of 2 times h bar, okay. And then what I said is, let's drop a line down here, this dotted line here. And this dotted line, do you see how this dotted line runs parallel to the z-axis here? Okay, see how it runs parallel? And the dotted line is the length of that dotted line. Okay, the length of that will represent the z component. How much of the z component do I have there? And in that case, we chose +1, right? So that's just going to be h bar. Okay, the length of that's h bar. And then I said, well, what we can do is, because I know that this right here, this angle right here, is 90 degrees, I could just use basic trigonometry to find the angle here, which we found out was 45 degrees, which allowed us to find the angle of this other triangle here, of course, which is 45 degrees. And we said if we did that, we could interpret that, and let me choose a different color, something, choose a brown here. And I said, so if we did that, what we could do is we could say that the z component of this, okay, the z component of the angular momentum, okay, like that. I'm going to draw another line there, is 45 degrees off of the z-axis. And I said, so we can't know the angular momentum exactly, but what I could do is I could draw a little cone here. Okay, I could make a little cone out of this, and I could say that that angular momentum could be anywhere along this circle here within that cone. Okay, so the angular momentum is 45 degrees off of the z-axis, the orientation of it, but I don't know exactly where. It could be here, it could be here, here, but it has to be within this circular area that's 45 degrees off the z-axis. And then we said, well, if this is positive here, right, then negative would be down here. So I could go ahead and put my z, just kind of extend the z down here. And then I could say, well, in that case, if I plugged -1 in, okay, -1 in for my value, what would that give me? Well, let's just go ahead and do that. That would just give me the same thing here, only it'd be the negative of this. So I would have something that looked like, let's choose brown for consistency there. All right, let me cover over that in brown. Okay, so I'd have something here that looked like this, which was 45 degrees off of the negative z-axis, and it would be the same thing. It would be kind of a cone, and there would be a circle there, and then I would have 0. Okay, so if 0 would just kind of be like right in here, and that would be the orientation of the angular momentum. Okay, fair enough. So you could imagine, and I'm going to go ahead and just clear this here real quick. You could imagine a situation where if you were to look at all 3 of the configurations that the orbital could take, I've got to find out where my little clear is, my little clear option. Boom, there we go. All right. So you could sort of imagine that if we were to look at all 3 orientations of the p orbital, you could imagine, you know, something that kind of like a torus like this here, a torus like this here, and then maybe if m sub l equals 0, you might actually have a proper p orbital. Okay, so you might have a m sub l equals 0 equals +1, -1. Okay, you might imagine orbitals that look something like this here, which is rather counterintuitive if you think about it, because that's not what we're used to seeing at all. We are not used to seeing orbitals that look like that. But what I want to do now is I want to go ahead and I want to open a program called Atom in a Box. All right. So I'm going to open Atom in a Box here. All right, and I'm just going to change the display to give you guys some colors here. And the cool thing, I'll do 64 samples. That'll make it, hopefully that won't slow the computer down too much. Phases of color, boom, there we go. And let's just adjust our gamma here. Nah, I don't want any steps. I'm good with that. I'll make my brightness multiplier, let's see, brighten it up just a bit more so hopefully we can see that better. Okay, so what I'm going to do is I'm just going to start this off. So basically what I have here is this is a cool program that actually solves the time-independent Schrodinger equation. It solves for that, and all you have to do is put in your, right up here, you just have to put in your quantum numbers. It's N, L, and M, and you can see I have psi, my wave function within a ket vector. You don't have to know what a ket vector is. That's Dirac notation, but basically that just means, hey, it's quantum mechanical. It's a bit more complicated than that, but there you go. And so it's excuse me, it's psi, N, L, and M. So this first one is N, L, and M. So what I'm going to do is I'll just start. Boom. We'll drop this down to a 1s orbital, right? So I'm going to start there. And what I'm going to do is I am going to go ahead and solve the Schrodinger equation using this atom in a box. I'm going to solve that, and what I'm going to do is I'm going to go to the second energy level. Okay, so right now I have a 2s orbital, but what I'm going to do is I am going to set L at 1, and I'm going to keep M sub L 0. Okay, so I have N equals 2, L equals 1, and M sub L equals 0. Okay, and we get, if I pull this up here, we get an orbital that pretty much, let me just go into full view here. Boom, there we go. Okay, so we get an atomic orbital that looks pretty much like the cool little p orbital that we're used to seeing, right? That's what we're used to seeing. We're used to seeing two dumbbell-shaped things, these areas of probability density, high probability density, with a node in between them, and you can see that this is lined up along the z-axis. Okay, so this is what we see. So what I'm going to do now is I'm going to change M sub L, and I'm going to make it positive 1. So I have kind of this circular torus looking thing here, and you can see it's kind of rotating this way. And then the different colors are an indication of the phase of the wave. And then if you'd imagine that if I went negative 1, I would have a circular torus looking thing. It would probably be rotating in the other direction because the angular momentum is aligned in an opposite direction. And what do you know? There you go, negative 1. 2, 1, negative 1, right? Well, that's cool. That's all well and good. But the problem I have is that does not look like the atomic orbitals that we use in chemistry. It just doesn't. So the question is, how in the heck can we get proper p orbitals? Because if we can get p orbitals that align along the x, y, and z axis, it's much more convenient dealing with those orbitals when it comes to chemical bonding. It's much more intuitive when you think about bonding in line with an orbital. Whereas the what we call the physicist orbitals are less convenient. Well, what we can do is we can take that angular momentum and kind of, well, not the angular momentum, we do, but what we can do is we can take, so here I have my m sub l's, right? I have +1, I have 0, and I have -1, okay? 0's okay, that's a-okay. Well, what I can do is I can take what are called linear, I can take linear combinations, all right? I can take linear combinations of the +1 and the -1, okay? I can combine them and I can make new atomic orbitals that are superpositions, and I've actually have done videos on superposition and how you can add and subtract waves, because that's kind of how these electrons are acting, very much like waves in the atom. So if I take a wave like this, and then I take a wave like this, and both waves are in phase, their peaks and their crests are at the same, and I interfere them, I'll get something like that. Whereas if I take a wave like this and a wave like this, okay, they can they'll interfere and they'll be that. Or if I take waves that are out of phase, I can get destructive or constructive interference. Same thing here. I can take super linear combinations of the +1 and the -1 state, and I can make superpositions, put them into superposition, and I can make different orbitals, and that's allowed. That's allowed in quantum mechanics, because as long as I follow, the basic rules and postulates, things that I'm not really going to talk about here. But I'm not changing the energy, right? I'm not changing the energy level. I'm not changing the total angular momentum, right? Okay, so I'm not fundamentally changing the energy and the total amount of angular momentum that I have in the pool, in the bank, if you will. I'm just kind of mixing and matching what I have available to make atomic orbitals that are much easier to work with. And this is something very strange. This is one of the strange things that comes out of quantum mechanics that really doesn't jive with what we're used to in classical mechanics. So what I'm going to do is I'm going to open Atom in the Box up again. And what I'm going to do is I'm going to hit this little superposition button down here. Boom. All right. Now, what it does is it's going to bring up psi here in a ket vector, and psi equals, and here what I can do is I can designate what orbital. I can make an orbital here and an orbital here, and I can put these two into superposition, and you can see I'm getting a warning that these are not orthogonal, which is not a really concept I'm going to talk about, but you actually, when you put things in superposition, they have to be orthogonal, they have to be orthonormal solutions or sets for this whole superposition business to work. And frankly, if we're only dealing with 3 quantum numbers, we know there are 4, but if we didn't know that, this would basically be putting electrons in the exact same quantum state, and we don't want that either because of the Pauli exclusion principle. But we know that we can actually do this because we have a 4th quantum number, but we're not dealing with the spin here. So what I'm going to do is I am going to select a 2, and then I'm going to go 1 for a p orbital, and then I'm going to make a +1, and then in this orbital here I'm going to 2, 1, and I'm going to make this -1, and look what just happened. Boom. When I put the 2, 1, 1, 2, 1, -1 into superposition, I'm able to get the nice, cool-looking chemist p orbital that we're used to seeing here, and that's exactly what we've got, and that's exactly how we are able to create, quote-unquote, p orbitals that are much more convenient to work with when it comes to chemical bonding. But the original solutions for these orbitals did not have probability density plots that looked like this. We had to take superpositions of the m sub l in its -1 and its +1 state to get to these chemist orbitals. Okay, guys, hopefully you found that helpful, and as always, thanks for hanging in there.